So welcome everyone to the 11th CRM-PIMS Probability Summer School. This sequence of summer schools launched at UBC by PIMS in 2004 and occurring not quite yearly, but close to yearly between then and now. It's a great pleasure to be involved in organizing and lecturing at this incarnation of the summer school. These events were very formative for me as a student, junior researcher in probability, and I hope that they'll be both pleasurable and informative for all of you. We have about 150 or 160 people signed up this year at various career stages. Obviously, the format is a little bit different from previous in-person schools. One of the advantages of that is we can reach a broad audience across the world, whereas we were previously limited in capacity by the physical space and the logistics of hosting people at UBC or in Montreal or in Washington, the various places that the summer schools have occurred in the past. But it's a great pleasure to be welcoming you all, and I hope to get to know you better over the course of the month. There are two main courses delivered by Jean-Christophe Mourrat and myself, as well as two mini courses delivered by Sarah Pennington in week 2 and Kavita Ramanan in week 3. I hope that you'll attend as much of those as you can. There is various information about the summer school on the course website. Both Jean-Christophe and I have notes in various stages of completion, and there are links to those notes if you want to take a look at the material that we're presenting in our courses. I've also made a course website with exercises for some of the students who are either taking the course for credit at McGill or are attending through MSRI, who have sort of regularly scheduled exercise sessions, and I've emailed you all about that. There are also some students or some participants who've indicated interest in working on exercises in groups with other participants, and I've emailed sort of provisional groups to you, trying to keep students in similar time zones working together so that you can manage to schedule your group work efficiently. If anyone's interested in participating in those sorts of group exercise sessions but hasn't signed up yet, send me an email at the summer school email address, which is summerschool@math.quebec, and I'll write that in the chat as well. That is a legitimate email address. .quebec is a valid domain ending, in case you're confused by that. Great. The videos are all being recorded and will be posted publicly, and are also being streamed live on YouTube. So if you don't wish to be recorded, then we ask that you turn your video off and don't use audio. If you are welcome to use those things, but if you don't want to be recorded, that's fair warning. I think that was all. Oh, one more thing. We'll shortly send out a demographic survey for participants. This is important for the funders of the school, so I'd really appreciate it if you could all fill it out, and I will periodically bother you about that. Last year, some of the organizers of this school, as well as some of the people who organized the online open probability school, we had great turnout for that. About 800 people signed up for the mailing list, maybe 850, and we only got about 80 people filling out the response survey. So that was kind of disappointing. I'm hoping that we'll get a higher percentage response to this year's demographic survey. Okay, with that out of the way, it's a great pleasure to introduce Jean-Christophe Mourrat, who's an associate professor at NYU on leave from CNRS, who is lecturing from France and will tell us about mean field disordered systems, and I'm very excited for his course. Thank you so much for agreeing to lecture, Jean-Christophe, and I'm just going to spotlight you for your lecture.
Thank you very much. So let me start to share my screen just to make sure things work. Yeah, thank you very much for the introduction, and most importantly, thank you very much for inviting me. I really appreciate enormously to be given this chance, and I'll do my best to be worthy of that chance. So yeah, as Luigi just said, there is a material relevant to the course on the summer school's website, and also on, like, you can also find it through my personal webpage if you want. So yeah, this includes handwritten notes that I wrote down to prepare the class, the problem sets, and also the slides I'm writing during the class I will put in there as well. And there's also there are also people who volunteer to write transcripts for the lectures and to possibly also write solutions for the problem sets. And you can view this, like there is also a link so that you can view the current status of this document. All right, so let me now start with the actual content of the class. So yeah, the title is Mean Field Disordered Systems, a PD approach. In some sense, for me, the long-term goal of this course, and more generally, is to make progress on our understanding of spin glasses. And I say long-term, both in terms of how the class will be structured for these 4 weeks, because we will talk about many other things or many other models before we talk about spin glasses. And also it's long-term in a broader sense, in the more research sense, because at present, the results I would like to obtain are not yet there. So I only have partial results concerning spin glasses. So it's, it's also long-term in some much more longer time frame. And so just to clarify, first of all, what spin glasses are, let me introduce possibly the simplest model of a spin glass, which is called the SK model. So SK stands for Sherrington and Kirkpatrick, the physicists who introduced the model. So one way to think about this model is to imagine that you have n people, which we can label as using the integers from 1 to n. And you want to create 2 groups out of these people. So maybe there will be a group of +1s and a group of -1s. So in order to represent the assignment into 2 groups, it suffices to reveal a vector of +1 and -1 of length n. Okay, so I'm going to write sigma for this vector, and okay, this is shorthand, like this +-1 is shorthand for 1, -1. So if I give you this vector of +1s and -1s, it prescribes for us an assignment of this group of people, of this set of people, into 2 groups. And in the description of the problem, you're also given parameters j, I, j. So for each I and j between 1 and n, you're given this coefficient j, I, j. And okay, so maybe j, I, j characterizes the quality of the interaction between individuals I and j. By this, I mean that if Jij is positive and large, it means that I and j really get along well together. They would like to be in the same group. While if Jij is negative and maybe very negative, then it means that I and j dislike each other and they would really rather be in different groups. Okay, and for the purpose of this model, I'm going to assume that these coefficients are independent and identically distributed, given by standard Gaussians. Okay, so assume Jij are independent standard Gaussians. Okay, and now you have a well-defined optimization problem that you can try to solve, because you want to find this assignment. You have your objective function, which is to maximize overall happiness. And overall happiness means that you want to maximize the following function. So for each configuration sigma, we are going to compute the sum over all pairs of jij times the indicator function that individual I and individual j are in the same group, which we can write as the indicator function that sigma I is equal to sigma j. Okay, so this is the object that we would like to maximize so that we discover the assignment into two groups, which is maximizing overall happiness. And equivalently, so for a bunch of different reasons, I'm going to explain later, people usually prefer to write the following function, which corresponds to the same optimization problem. So instead of writing this indicator function, people like to write sigma I, sigma j, just a product of sigma I and sigma j. Okay, so if I is equal to j, this indicator function is equal to 1, and this product is equal to 1. And if it's not the case, then the indicator function is equal to 0, while the product is equal to -1. So you see that there is a clear correspondence between the two optimization problems. So with that loss of generality, you can decide you focus on optimizing the second function. And it's more customary to do this in the setting of spin glasses. So I'm going to actually focus on this function. Oh yeah, and I'm seeing that there's some activity in the chat. So because I was perhaps a bit stressed out for the beginning of this conversation, I did not pay attention, but normally I try to keep an eye on the chat. So feel free to write things there. And yeah, like Omer and other people have already answered the question, so I'm not going to comment further. But yeah, I'll try to keep an eye on the chat. So yeah, really feel free to write questions. Okay, so is the thing clear so far? So J and J are independent standard Gaussians. And I'm wondering if I can maximize the function that is on display on the last line of the slide. Yeah, so the difference between the two functions is a constant. I mean, it does not depend on sigma. So if you optimize one function, the sigma which realizes the maximum for one function is the same as for the other. And in fact, also the values of the function, they are not the same, but it's very easy to understand one from the other. I think you go from one to the other by just computing the sum of the JIJs, and maybe there's a factor of 2 also, but it's quite straightforward. Okay. All right, so why is this question not obvious? The reason is that the JIJs can be positive or negative. So well, the consequence of this is that even if you have a very simple situation with just 3 sites, the following can happen. So let's say this is site I, site J, and site K, and there are pairs between each of these points. And let's suppose that the Jij here is positive. So you would like that I and J be in the same group. And maybe this coupling, the capital J between J and K is also positive. So you will also like these two guys to be in the same group. But it so happens that the interaction between I and K is negative. And so in fact, you would want these two guys to not be in the same group. It's kind of clear that you cannot reconcile all of these constraints at the same time. Right? So you have to make a trade-off. And in fact, if I just give you the signs of these interactions, you cannot know what is even the best thing you can do. Okay, so it's not obvious what is the best assignment for sigma. So you see, if the JIJs were all positive, for instance, we could decide that we put everyone in the same group, and this maximizes overall happiness. But because some want to be in different groups, this does not happen. So in general, we can call this frustrations. So there will be, in general, some pairs which maybe they are in the same group, but they would like not to, or they are not in the same group and they would like to be in the same group. So even at the optimum, such things will typically happen. Okay, so the frustrations is an inherent part of the problem. And really, in my opinion, frustrations is really what should define what a glassy object is. Okay, so each time you look at some object that you try to optimize, and you have these complicated constraints that make it difficult to discover the optimum, you can think of this as being a glassy material. Okay, so that's where the word glass comes from. So if you think in terms of progressively trying to discover the optimum, then you see that sometimes in order to reach a better configuration, you'll have to make changes that will at first look detrimental to you. There's no easy step-by-step way for you to discover the optimum. And this really, even more than having random interactions, this really is what glassy means. Okay, and while I'm at that, in the title, there was also mean field. And mean field means that the geometry of the set of units that we look at is very simple. So here it's the simplest possible because every unit interacts with every other unit. Okay, so there is basically no geometry. And so instead of saying no geometry, we say mean field. Okay, well, that's at least a small shortcut. All right, and so just before I continue to describe this problem of finding the optimum of this function, I want to extend this question a little bit. So instead of only focusing on the maximum, I also want to discuss, let's call them soft versions of the maximum. So also soft max. What do I mean by this? So I want to look at the following object. So yeah, I'm putting some normalization. I'm going to sum over all configurations this exponential of this function. I'm going to soon start to call it the energy function. Okay, this mapping over there, this mapping here, that which to which sigma associates the sum of jij, sigma I, sigma j. I'm going to call this the energy function. And so yeah, I want to look at the sum over all configurations, all sigmas of the exponential of this energy. And you see in the exponential, I put some 1 over square root of n. So I'm not going to explain, but this just take it for true for now. This makes it so that in the exponential, typically the object is of order n. Okay, so if you do that, then as you slide this parameter beta, you can interpolate between. Okay, there's some very easy case when beta equals 0, you're just summing over all configurations. This is really not looking at the energy function. And when beta becomes very, very large, on the other hand, this sum will be essentially completely carried by the few terms which maximize your energy function. Okay, and so we can use this beta to interpolate between problems which are more or less concentrated around the few configurations that reach the maximum. So for very large beta, you can think of it as a soft or smooth version of taking the maximum function. Okay, and I want to understand this behavior in the limit when n becomes very large. So I told you that the object in the exponential is over the n. So if I want this object to stabilize as n goes to infinity, it seems reasonable to take the logarithm and then divide by n. Okay, so that now this should be of order 1. And also, if you pay attention, you see that this object is still random, right? It depends on these jij's here, which are standard Gaussians. But in fact, the fluctuations of this object are very small. So you can just stop to think about this. And I'm going to take the expectation so that we don't worry about these fluctuations. Okay, and so the question I want to ask is, what is the behavior of this when n goes to infinity? This I'm going to call the free energy. So it's, there are some, I introduced this problem as some purely optimization problem, but there are connections with physics. And for this reason, this object is often called free energy, or at least I will call it that way. Yeah, so the question is, what is the limit when n goes to infinity of this object? And the surprising thing is that it's actually a very difficult question to answer. I say it's surprising because the question we ask, at least in my mind, is relatively simple. I mean, I introduced this maybe somewhat more complicated version with this exponential, etc. But in terms of the maximum, it's really relatively modest. No, we take these independent Gaussians, we look at the sum of j sigma I sigma j, and we try to look for the maximum. So just to answer the question in the chat, the thing is that the Jijs are centered, they have mean 0. So you should not think that the sum is of order n squared. Okay, it's there will be stochastic cancellations because the Jijs are centered and of mean 0. And moreover, I would like the exponential, what is inside the exponential, to be of order n. And the reason is that when I sum over sigmas, there are 2 to the n terms. So I want the cardinality of the sum to be roughly on par with this exponential here. So you see this 2 to the n, I want it to be balanced with some exponential of something of order n. Okay, so I don't explain completely why this is the right normalization, but at least it kind of ballparks what you want to achieve. All right. And so, yeah, I was saying that the surprising thing is that the answer to this question is actually complicated. And it was predicted by a physicist named Giorgio Parisi in 1979. So what he predicted is the limit of this object as n goes to infinity. So proposes a formula. For this limit. And in fact, when Parisi proposed this formula, initially, even within the physics community, it was actually relatively controversial that this proposal was correct. And I'm not going to fully write down what the formula is, but I'm just going to write the beginning of it. So it starts by saying that it's an infimum over the set of probability measures of a certain functional. And I'm not going to write down what is the functional, but it's not immediately intuitive, let's just say. And part of the reason why physicists found that very surprising is that it's quite well known, and I saw someone in the chat mention large deviations at some point. And I think the comment I'm going to do is related to this. It's well known that expressions of this sort you can rewrite as supremum over probability measures. So physicists would think of this as some energy entropy optimization problem. If you like to think about large deviations, you can think that there's this sigma, which you can think of as independent Bernoulli random variables, plus or minus 1. And maybe you're trying to find a strategy for the sigmas to maximize this quantity. And this strategy could be described by a probability measure describing what you want sigma to do, and then you would try to take the supremum over these probability measures. Anyway, whether or not what I just said makes sense to you is not very important. But what is important, or what I just want to underline here, is that it's very natural to write the expression here, this free energy, as a supremum over probability measures. But what Parisi proposed instead as a limit is an infimum over probability measures. So that's what part of the reason why the formula was initially surprising and to some extent controversial. But over time, physicists understood more and more of this this picture of Paris's proposal, and ultimately were convinced that it was in fact correct, despite this initial surprise. And later, mathematicians put a final confirmation to this because they actually proved that this formula is correct. So this came in several stages. So first, Guerra proved one bound between the limit and this infimum formula. And then Talleyrand proved the converse bound. So then the full proof was obtained in 2006, shortly afterwards. And then another very interesting development came that Dmitry Panchenko generalized this result to a much broader class of models, and also arguably gave a more conceptual proof of the result. So that's all very nice. And the overarching goal of the course is to describe my attempt to understand models which go beyond this class. And one, so first of all, I have to say, as I already said earlier, this is not yet a complete theory. I only have partial results so far, so it's research in the making, let's say. But I thought it would be interesting to speak about research in the making, because if you at some point want to join, then it's nice to know that there are many things that remain to discover in this area. And just I'm going to, instead of trying to discuss general classes of models, I'm going to single out one model which I believe is interesting, and for which I do not know how to answer the similar question. Okay, so, and this model is a bipartite version of the model I just described. So let's say, let me write that the course aims in particular at understanding the following the bipartite version of this model. So what does it mean? In the model, in this SK model we discussed, each unit interacts with any other unit. In the bipartite version, on the other hand, the units will be organized on two layers, and we will have interactions only between one layer and the other layer. So you can think of a picture of this sort. Here are some units. Let's say there are n of them, and then there are further n more of them below. And these couplings Jij's, they are going to only go from one layer to the other layer, like this. Okay, I cannot draw all of the links, but you get the idea. Yes, so the main point is that links like this are not present. Okay, so if you want a more formal definition, you can think that in this bipartite version, the configuration is represented by two components, each in Rn. So it's in Rn cross Rn. And the energy function will be the sum of Jij sigma 1i sigma 2j. Okay, so overall I and j between 1 and n. Okay, and again, Jij here are independent standard Gaussians. And to my surprise, at least at first, I realized that for this relatively modest modification of the original model, we do not know how to identify the corresponding free energy or the maximum of this function, if you want. At least in this limit of n going to infinity. And yeah, so my goal is to present steps towards an answer to this question. Yes, yes. So there's a question in the chat about whether or not the sigmas are +1 or -1. That's true, yeah. So I wrote Rn cross Rn because you could imagine using this as a function defined everywhere, but then you try to optimize it over ±1 to the n cross ±1 to the. Yes, yes. Thanks for this question. And more generally, maybe you want to consider other reference measures, let's say, but let's stick to ±1 to the n. All right. So maybe at this stage you wonder why you should be interested in this question. So I'll try to discuss why I find this question interesting. Well, the first thing is that here I describe a model with 2 layers, but in fact, as I said, I think either we succeed in describing this free energy for this specific model, and then all other models in a much broader class will be covered, or just nothing works. So to be more precise, if you like to put more layers into your model, let's say 15 or 100, then the same mathematical problems are present. So, and okay, that's the first remark. And secondly, having elementary units put into many layers is fairly popular these days in machine learning. And okay, yeah, when you try to do machine learning or when you do neural networks. And I do not claim that this is immediately going to be relevant for neural network questions, but at least it seems to be a reasonable question to ask to know what a typical neural network, one where these weights will be taken at random, is doing. So, or at least maybe if I put it the other way, if I cannot even answer the question of what happens when these weights are just chosen randomly and without any correlation, then perhaps there's not much hope to do more sophisticated questions. So that's one motivation. Another motivation is that there are, so this is one model among several, and I could describe other model problems which have similar features. For instance, one which is also very easy to describe is if you decide that you do intersections of random half spaces. Okay, so just before I move to that, I see another question in the chat about what is the structure of the connections between particles in different layers. Yeah, so I put connections between, so it has to retain, the geometry has to remain relatively simple. Okay, by which I mean, maybe there are a few types, and then the graph of connectivities only depends on the type of your unit. So let's say you're allowed a finite number of types, let's say 5, I don't know, and each type describes one layer, and then you can prescribe that each item of type 5 is connected to each item of type 4, and then each item of type 4 is connected to items of type 5 and 3. Things like this are allowed, okay? But you're not allowed to put things on the grid, for instance. Okay, like if you want to create a model on ZD, then I have nothing to say about this model. Does that clarify the question? Okay, so yes, I was trying to describe other models. So another model which is easy to describe in words is if you take intersection of random half spaces that go through the origin. So you just pick a random direction. That defines for you a half space, and then you take another one at random, and then another one, and you continue like this. And if the dimension is n, and you take a number of half spaces proportional to n, you can ask, first of all, is the set empty? And if it's not empty, what's the volume fraction that it occupies? And it turns out that this question is very similar to to these spin glass problems that we're discussing here. So other problems in computer science are called constraint satisfaction problems. Maybe I won't take too much time to describe this. Maybe if you've heard of the Hopfield model, it's also, in fact, extremely close to this two-layer model that is described here. In fact, you can, like if you look at the marginal on one layer, it's basically a Hopfield model. And the Hopfield model is a model for memory storage and retrieval. Other motivations include the statistical inference, and this we are going to talk about much more in the class. So yeah, stay tuned. I'm going to explain more about statistical inference in a short while. Okay, so that was one question you could ask. Another question you can ask is, why should we focus on this specific question of computing the free energy? Okay, why should I want to compute this quantity? And my answer to this question is that I believe that this is the simplest thing you should try to do when you start to look into the problem. Like, I believe that if you want, again, to put things the other way around, if you do not manage to compute this limit, I believe you're going to be extremely limited in your ability to say anything about the problem. So, that's kind of a belief I have, let's say, and you can disagree with this, and surely it cannot be true in a literal sense. There are plenty of things one can say without talking about the free energy, but I believe it's let's say it's some sort of a threshold that we need to pass, and once we manage to pass it, maybe it opens possibilities for further explorations. So maybe one way to think about this free energy is that it gives you some analytically convenient way to probe the geometry of the landscape of this energy function. Maybe it's by sliding this beta, it gives you some way to try to describe in some analysis sense the geometry of this energy landscape. And perhaps one would find more interesting to describe the behavior of concrete optimization algorithms on this landscape. So at the beginning, I described an optimization problem. I was like, okay, I'm trying to maximize this function. And so far, I only discuss theoretical questions like what is the optimum, but I do not discuss how do we find the optimum. And maybe you find this question more concrete because you think, this is what I really want to understand. In practice, I want to know how to find the optimum in these complicated landscapes. And my claim here is that I think it will be a necessary first step for you to understand this free energy. And at least for those models we already understand, like the SK model, this has been true indeed, that if you want to understand good optimization algorithms for this SK model, for this problem I introduced at the beginning, you have to rely on your understanding of the free energy. So I'm not going to discuss further these optimization problems for spin glasses, but I think it's useful to keep in mind that understanding the free energy can be useful also for quote-unquote practical purposes. All right, so maybe other questions so far? Maybe I'm thinking that maybe it would be a good time for a break. I think having a little break in the middle would be nice. Other questions so far? Yes, so there's a question about whether these JIJs, I said they are Gaussian, and standard Gaussians. And the question is, can we take other distributions than Gaussian? And the answer is yes. And in fact, compared with the question I just discussed, it's more accessible to show in advance that the free energy will not change if you replace Jij by other random variables which are also centered and have the same variance. So in fact, the really important assumption is that expectation of Jij is 0 and the variance is 1. And maybe they have sufficiently many finite moments. I forgot how many, but maybe 3 is probably enough. Maybe 4. I think 3 should be enough. So before you manage to compute the free energy, you can show that any model which comes with these random variables which are independent and have mean 0, variance 1 will converge to the same free energy as the one with the Gaussians. So it's convenient to show this first, and then we can say, okay, now we're done. We can focus on the Gaussian case. Yes. So there's a question about. Okay. So first, so why the free energy like this? Yeah, I only briefly kind of gave some impressionistic view, but I claim it's a good way to scan your energy function if you want, like to try to explore it. When beta is very large, this is really talking about the maxima of your energy function. When beta is very small, it's also an easy quantity to understand in some sense, because when you sum over the sigmas, basically all of the terms contribute. So it's like the underlying, like if you think of these sigmas as being weighted by these exponentials, you can think of this as a probability measure proportional to these exponentials. Basically, this probability measure is uniform over all configurations. So it's also kind of easier to understand. And then, hopefully by some sort of maybe analog of a renormalization argument, you can hope that by sliding the beta, you're going to, move from this small beta zone where you understand things relatively easily, progressively towards a large beta zone where things become perhaps more interesting, but also more difficult. Yes, so the choice of scale, I did not fully explain, but maybe I can try to explain better now. So I think initially, let's take it for granted that I want this quantity to be over the n. But when I say over the n, I mean for a typical, for one of these terms which really contribute to the sum. So let's say, for instance, I look at this quantity. I look at the maximum over sigma of this quantity in the exponential. And I want to make sure it's over the n. So, okay, so maybe let me scroll down for a second. So I'm asking, what is the behavior of this maximum over sigma of sum of jij, sigma I, sigma j? So, so here I'm just asking in terms of what's the right power of n. So it's n to some power, and what is the power? And it's not super difficult, but it's not super easy either to answer this question. So I'm going to change the question into something easier to answer, if you don't mind. So imagine instead that I'm trying to answer the question of what's the behavior of the maximum over all of these of E sigma, where, okay, so I should say for each choice of your sigma, this sum, so it's a sum over n squared terms. So this is a Gaussian, and its variance, okay, I have to, so each term has variance 1, and I sum over n squared, so its variance is n squared. Okay. So here I'm going to multiply by n, and then think that these are IID Gaussians, standard Gaussians. So I'm ignoring correlations, just as a first guess, let's say. So they are not the same problem, but just as a first guess, I'm trying to understand how this behaves. So if you think that you have 2 to the n independent standard Gaussians, and you look at the maximum, then this is not too hard to show that the order of magnitude is square root of n. So it's new E sigma are just new random variables which are independent standard Gaussians. Okay, which I'm just using as some toy problem, which I think about in my in my head before answering the true question. Okay, so E sigma are independent standard Gaussians, and I'm asking myself what's the behavior of this maximum. So I claim that this is over the n to the 3 halves, because there's one n here, and then when you look at the maximum of k standard Gaussians, this behaves like square root of log k. Okay, I mean this is this you can do. This is an easy exercise. Okay, so if you ignore correlations in this first question here, then the answer should be also n to the 2/3. Sorry, 3 halves. Okay. Okay, I feel I confuse people. So I'm asking myself what's the behavior of the maximum of the energy function. The free energy is containing this term in some sense, right? Like the free energy is this object. Oops. But in particular, it contains the sigma which realizes the maximum, right? And so you see that by dividing by square root of n, I make sure that for the specific choice of sigma which realizes the maximum, what is inside the exponential is over the n. Does that make sense? I did not fully justify it, but I tried to justify it a little bit more than before. And today is introduction day, so I don't want to go too much into rigorous proofs. But then you can try to do a first moment, second moment argument. I gave an argument that ignores correlations between these JIJs, between these. Sorry, this is a maximum over a lot of random variables, and they are correlated, and I'm ignoring these correlations. So you can make a first moment, second moment argument that shows that indeed the order of magnitude is n to the 3 halves, but I'm not going to do it right now. Does that make sense, or please say something in the chat if it makes sense. Okay, good. Okay, so by dividing by square root of n, I make sure that for the maximum and maybe the second maximum also, like the first few biggest terms, the quantity is over the n. Okay. The JIJs are independent, but then when I ask about the behavior of the maximum over all sigmas, if I think of each of these random variables as indexed by sigma, by this vector, then if I change sigma to tau, let's say these two things will have correlations, right? Because you use the same JIJ random variables to define the two terms. Okay. So as I vary the sigma, these have correlations. But as an analogy, because I want to give a quick explanation, I replace this by a maximum over independent random variables. All right. Okay, so maybe we'll take 2 more minutes of break for real, and then I will resume the conversation. Yes, so Luigi gave in the chat a lower bound thing, and the argument I gave, you can show that comparing with something which has no correlations gives you an upper bound all the time. So in fact, okay, so you have to justify what I just said, but that's true. And then you have the two bounds. Thanks, Luigi. Yeah, another question in the chat is, if we don't care so much about the JIJs being Gaussian or other distributions, why don't we use discrete random variables like +1 and -1 with probability 1/2? That's a fair question indeed, but it turns out convenient to use Gaussians because, yeah, you'll see later, but we want to use something which is a little bit similar to Ito's formulas, or it will come in the form of Gaussian integration by parts. And these are somewhat harder to see with the discrete random variables. So it's analytically more convenient to use the Gaussians. Maybe one way to understand this is that you see, I want to, in fact, instead of, I wrote this beta in front of the sum of Jij, sigma j. But in truth, very quickly, I'm going to want to, instead of writing beta, I will want to write square root of t. And then you see that you have this square root of t times the Gaussian, and this evokes Brownian motion. And, we will not use really Brownian motion encoding per se, but all the things you can do with Brownian motion we'll be able to do also with these Gaussians, because after all, square root of t times a Gaussian is some Brownian motion. It's relevant because we really are interested in trying to slide this parameter t from low to high. So, in particular, we will want to differentiate in t, and so you will have nice Ito type formulas when you use Gaussians. All right, so let me continue. So as I said, the spin glass thing it's possibly my main motivation, but in fact it will come only quite late in the course. And before we talk about spin glasses per se, we will be busy with two other models, or two other classes of models, I should say. The first one is the Curie-Weiss model. So you can obtain it from the SK model by simply setting Jij to be equal to 1 instead of the Gaussians. So here it's no longer a centered variable, but there's no longer this effect of the Jij's being of varying sign, for instance. So in particular for this problem, finding the maximum is very easy. You just set all the sigmas to be equal to +1. But computing the free energy is, okay, at least slightly less easy, but also not so difficult. And we will also study generalizations of this model. So this one is really our training ground. We're not. It's nowhere near being near the frontier of research, but it will be extremely useful for us to develop powerful techniques to deal with later models. So that's one model or class of models, and the second class will be models that come from statistical inference. So inference means that you observe a noisy signal and you try to infer or recover the signal. So in particular, we will focus on the following problem. We consider following problem. So we have a vector x bar of independent and identically distributed random variables, which we are going to only observe. So we observe a noisy version of x bar transpose. Okay, so this is a matrix. Maybe explicitly it writes x bar. Oops. x bar I, x bar j. Okay, so let's just say you observe this matrix plus noise, and noise is like on each coordinate there's a bit of noise. Okay, so you observe this noisy thing and you try to recover that thing. Okay, so you observe a noisy version of x bar transpose, and you try to recover x bar transpose. Okay, so we try to recover x bar transpose. And in fact, we will see that there is a very interesting phenomenon similar to things we will observe for Curie bias and also later for spin glasses, is that there is a phase transition in the problem. So what that means is that what we will show is that when the signal to noise ratio is low, so meaning there's a lot of noise in your problem, basically you can, in the limit of large N, you can recover essentially no information about your signal. So I will make this more precise later, but in some very precise sense, you cannot recover any useful information about the signal. By the signal, I mean this vector x bar. And then at some point, when this signal to noise ratio passes a threshold, suddenly you start to, it starts to be possible to actually recover meaningful information about the signal. And we will nail down where this threshold is. And it's not just in terms of the power of n. Like we will say, at the right scaling, this transition happens for signal to noise ratio equals 1 or 0.3, or we will give an exact characterization of this threshold. And also, when we are past the threshold, we will identify exactly how much of the signal we can recover. And so that will be the questions that are of interest to us. So this is a more contemporary research. And this problem of recovering this matrix x bar transpose, it has links with other problems which you can think of as community detection, for instance. So community detection is the situation in which you have again, two groups of people, but you don't know their identities, and it so happens that maybe there's still the group +1 and the group -1, and they form connections between each other, but they prefer to form connections between members of the same group. So maybe with probability something, let's say 0.1, they want to be friends with people within that group, and with probability 0.05, they want to be friends with probability with people from the other group. And you only observe the connections and not who belongs to which group. And you ask yourself, can you recover what the groups are? So these two questions are in fact very similar, as I will explain during the lecture. There are also connections. So this is, this matrix x bar transpose is a matrix of rank 1. And in general, you can discuss low rank matrices of a similar structure. And this also has connections with recommendation systems problems. And of course, it would not be there if it had no connections with spin glasses. So I already used this analogy with these groups belongings, both for talking about SK and for this community detection here. And it's not a coincidence. So there is maybe it's not immediately obvious here, but there is a connection between this question I'm asking and the SK model introduced earlier. And in some sense, this question of recovering this matrix of rank 1 is a simpler setting in which you can, again, train your skills, maybe with the hope of discussing spin glasses later. Yes. And so we have three classes of models in our hands now. We have Curie bias, we have statistical inference, and we have spin glasses, which I introduced at the beginning. And what's interesting is that for these three classes of models, I will want to approach the question of studying the asymptotic behavior using the exact same technique, which is this technique based on partial differential equations. So let me write this. These three classes of problems will all be analyzed using certain partial differential equations. Okay, from now on, I'm going to write PDEs whenever I need to write this. So more precisely, in all of these problems, we will identify something like a free energy. And I will want to relate the limit of this free energy to the solution of a partial differential equation. Okay, so we will relate the limit free energy with the solution of an equation which has the following form. Okay, so here the function is, so it's f of t and x, and t is a non-negative, and x is just a real parameter. And it's quite striking that, in fact, for the three models that I singled out, like SK model, Curie-Weiss, and the statistical inference thing, in fact, basically the same equation shows up, well, with a little twist for spin glasses, but it's almost the same for the three problems. And this will make us will bring us to some sort of a detour towards discussing the specific partial differential equations. So these equations are called Hamilton-Jacobi equations. And you see that if my purpose is to say that the limit free energy is the solution of this problem, it will be very important for me to clarify what it means to be a solution of this equation, and in particular to have a good uniqueness theory. Something that tells me sorry. So I see in the chat a question about the initial condition. So with some initial condition, which will be clear given the context. So the boundary condition here is only at time 0, right? So it is only the initial condition. And it's true that if you have a more advanced understanding, you perhaps know in advance that in some problems there will be a boundary condition, but it will be of Neumann type. But okay, I'm not going to speak about this now. And so we will have to understand how to say, how to speak about solutions of these equations, and how to say in particular how to identify in particular uniqueness for these problems. Okay, because after all, what we want to show is that something that I'm going to argue is almost a solution to this problem converges to the solution. And this is only more difficult than saying that two things that are solutions are the same function. Okay? So it will be important for us to understand how to say there is a unique solution to this equation. And this will rely on the notion of viscosity solutions to this equation. Yes. So I want to clarify from the onset that I do not assume that you know in advance anything about this. Okay, so the course, I aim it to be self-contained in terms of your knowledge of partial differential equations. Of course, if you know already some in advance, it will be helpful, but I do not assume that you know things in advance on viscosity solutions. Also, yeah, I have to apologize for writing that something with the Rademacher theorem as a prerequisite. In fact, this theorem will not show up in the lectures. So if you haven't struggled with this theorem, great for you. If you have, I'm sorry, this will not be part of the of our course, or at least only very tangentially sure, if ever. All right, so let me try to describe the outline of our 4-week course. So there will be, at least my hope is that there will be 6 chapters. The first chapter is about large deviations and a bit of convex analysis. So if you want, it's like some background knowledge, which I think is possibly useful to understand the sequel. So in fact, strictly speaking, large deviations will only be used tangentially in the sequel, but it's a very natural companion to statistical mechanics, and I would feel bad to speak during 4 weeks about statistical mechanics without even mentioning large deviations. So I'm going to be relatively quick on this and very informal. You will find in the handwritten notes rigorous proofs of the statement I care about. So yeah, I hope they are readable enough for you to parse. But yeah, if things are going a bit too fast for you in this chapter, yeah, it's good to know that large deviations will not be really very useful for the sequel. Okay, so just having some rough understanding of what it is, it will be enough. And I think it's also interesting that already when you do large deviations, we have this idea of looking for Laplace transforms, or something that in other contexts we could call a free energy. I tend to think of the free energy as some sort of Laplace transform. And when we do large deviations, it's similarly, the first thing we try to do is compute the Laplace transform, or the free energy, if we want to call it that way. And from that, we deduce large deviations. The second chapter, so this will be a very short chapter, maybe even just one session. And yeah, there'll be a bit of convex analysis. I mostly want to single out one result, which is this Fenchel-Moreau result about, if you take about convex duality. Okay, so if you take the dual of the dual, then you recover the function. And then we will turn to the Curie-Weiss model. So here I'm going to try to motivate its definition. And also, I'm going to explain that using large deviations, you can identify the free energy of this model. Okay, so I said large deviations will not be important, but the point is that Curie-Weiss model is so simple that I can use large deviations in order to solve it. So this will be unique to this model. For the 2 other classes of models that we are going to discuss, it will no longer be the case. So we have to devise another proof approach if we want to continue with the next models. So instead of directly going to the more difficult models, I'm going to stick with the Curie-Weiss model and try to develop a more robust proof strategy to the identification of the free energy. Okay, so just to recap, for Curie-Weiss, because it's so simple, large deviations give us the limit free energy essentially without much effort. But I want to develop a more robust proof strategy for this model. And I will also introduce generalized version of the Curie-Weiss model. Okay, and now I already said it earlier, but what we're going to do next is focus on this partial differential equation question of how do we talk about solutions to the equation I displayed earlier, the equation which is displayed now here. How do we talk about existence and uniqueness of solutions? So we spend some time talking about these equations. And we will see them arising very naturally from the Curie-Weiss model. So it will be, this name is viscosity solutions because there's something called the viscosity here. And in fact, the Curie-Weiss model is so nice that it even comes with this extra small viscosity before we pass to the limit. So it's, from the Curie-Weiss models to thinking about viscosity solutions to Hamilton-Jacobi equations, it's really very, very natural. And then we will develop the theory for this. And in particular, we will focus on uniqueness questions for the equation. So I will focus a bit less on existence questions, because for us, existence will be coming essentially for free, because we're trying to show that something converges to the solution. So we're not going to be lacking candidates. The problem is just to show that there's a unique possible limit point. But the existence of a limit point will not be an issue. So in general, yeah, the thing I most care about is how do we say there is a unique solution to this point, to this equation. Okay, so that will be the third chapter. Yeah, I skipped a question in the chat, but I find it quite advanced, so I'm a bit, yeah, sorry, maybe we can keep this to the conversation later. Then the fourth chapter is going to be, so coming back to, to generalized Curie-Weiss models. Oh yes, and I should have said, in chapter 3, we will also solve the Curie-Weiss model using this Hamilton-Jacobi equation techniques. But in the fourth chapter, next we will try to use the same approach for generalized Curie-Weiss models. And here we will find some surprises. So for a very long time, I was very puzzled by this, especially because I was facing these surprises for spin glasses, and it took me a very long time to realize that I could mimic these surprises on these simpler models. And they are very, I mean, when you see them at first, it's hard to explain at our current stage, but it seems that for generalized model, it seems that the thing that makes viscosity solutions work is coming upside down in some sense, which okay, for those who perhaps know in advance what viscosity solutions are, typically you introduce a small parameter times a Laplacian to build the approximation, and then you let this small parameter tend to 0, and you say the limit is the solution. And the way we define Hamilton-Jacobi equations, it is crucial that the limit is that the limit is plus Laplacian. It's a positive parameter which goes to 0 times Laplacian, because you use the maximum principle to perform the arguments. But in fact, for generalized Curie-Weiss models, sometimes it seems to come with a minus sign, and this is just I think it should ring alarm bells if we understand what viscosity solutions are, because the maximum principle will be just upside down if the Laplacian has a minus sign in front. So okay, if what I just said does not make sense to you, no worries, this will be clarified later. So we will have this surprise, and we will see how to overcome this surprise later. So we will identify a new technique to identify the viscosity solution to some equation, and the mystery will rely on the fact that the functions we care about are convex of functions of their parameters. So I don't say more about this, but this will be really the key new ingredient, that in fact convexity on its own can act as some sort of selection principle for pinpointing the viscosity solution. And so, okay, when we reach chapter 4, I will make a clearer sense of this, what I just said. And we will see that once we have this, generalized Curie-Weiss models also are solved easily. And therefore, we recover what we knew in advance from large deviations, but using this other proof approach. And once we have struggled through these 4 first chapters, it's time to reap the fruits of our efforts. So then we go to statistical inference. And here, so this is the model with this x bar transpose, of which we observe a noisy version, and we try to recover x bar transpose. And what will be very nice here is that all of the hard work is already contained in the previous chapters. So when we write down what it is that we want to show for this problem, you have to speak about this information theoretic limits of how can we recover the signal, etc. Once we identify the correct definitions and the correct analog of the free energy, all of the hard work has already been done, and we can conclude for the questions we care about here. Okay, so if some of you have looked into what I talked about in the OOPS summer school of last year, I mentioned this problem as well. And there I used a different proof strategy, one which is not based on viscosity solutions. And the main point of this new approach I'm going to explain here is that this one extends to also to generalized versions of this statistical inference problem, unlike the previous approach I had described. So for instance, if you want to do, when you do x bar transpose, it's something of order 2, but maybe you want to do, you could imagine situations where you observe something of order 3, for instance, x bar I, x bar j, x bar k, and maybe instead of something of rank 1, you would have something of higher rank, etc. So anyway, you can cook up many generalizations. And the main advantage of the proof strategy that is presented here is that it covers also these generalized models. And I should say that this rests on this selection principle that we will talk about in chapter 4. And this is joint work with Hongbin Chen. And Jiaming Xia. Oops, sorry. Jiaming Xia. Okay, and another advantage of this proof approach is that, also contrary to the one I explained last year, it has a chance to work for spin glasses. So it's not yet working really, but at least we can go further, and this is what I hope to explain in the last chapter of this course, so which will be on spin glasses. So here, as I said several times, the results are less complete, but still we can say some things. So in fact, I lied a little bit when I say that this equation here describes both, or maybe all of the Curie-Weiss model, the statistical inference, and the SK model. It's not quite true because, in fact, for the SK model, you have to. So this variable x, it was a real variable. It has to be replaced by a probability measure for the SK model. So in other words, now the solution is going to be, let's say, f of t and mu. So t is t in R plus, but the mu, it will be a probability measure on the non-negative half line. And so you see that it becomes a little bit more complex because the equation becomes infinite dimensional. If you want to describe a probability measure, you have to supply, I mean, it's not really a vector space, but the intrinsic dimension is infinite. So things will be more complicated. And yeah, so far this is still even research in progress. But what I hope to achieve is to first give you actually a complete description of the fact that the free energy satisfies the relevant equation in some approximate sense. Okay, so we will see that the finite dimensional, the finite volume, the finite n free energy essentially solves the relevant equation up to some error, which, okay, then I have to wave my hands to say that it's small. Okay, so at least we will do this derivation of the approximate equation completely. And then I will state without proof the bound that I have so far, which is relating the limit of the free energy with the solution of this equation. And yeah, as a final note, I also would like to say that as far as I understand, so here we will have some conjecture for what okay, I should say, I already said early that for the SK model, we know the free energy in terms of the limit free energy in terms of this variational formula, this inf over probability measures, etc. And through our study of Hamilton-Jacobi equations, we will see that when the nonlinearity in the equation is convex, like it's here, so this is the square function, the nonlinearity, we can always write the solution in some variational form. So here we can recover the Parisi formula from this equation using this connection. So solution to an equation with a convex nonlinearity maps to variational formula. But for the bipartite case, and that's really the boundary between models we understand and models we do not understand. So for the bipartite case and all these other models we do not understand, the nonlinearity in the equation is not convex, in fact. And so in this case, as far as I understand, in fact, there is no variational formula for the limit free energy. So as far as I understand, in fact, the only possible conjecture you can make for the bipartite model is phrased in terms of this equation, which I have not completely described yet. And just to give you a hint of, for the bipartite case, what the equation looks like. So for the bipartite case, it's perhaps not very surprising that we will have to use two variables instead of one. And so the equation for the bipartite case will look sort of like this. So we will have two variables. Maybe I can call them x1 and x2. Oops. So you see that this, instead of having this derivative squared, it will be split into these two things. And because pink glasses are what they are, again, we will have to replace these variables by probability measures. Okay, so then it becomes a relatively more difficult to talk about, but still with a short description. All right. Oh yeah. So another thing. So that's the end of my description of the outline of the class. One other thing I wanted to say is that there is material I prepared for the class that you can find on the website of the summer school or on my personal website. This you already know, but I think I want to stress now that I prepared probably too much material for the class, and you have to be aware of this. Okay, so for instance, for large deviations, my notes are, have rigorous proofs, etc. But tomorrow, probably I will only be relatively sketchy about the arguments. And similarly, perhaps more importantly, the thing I wanted to stress is that I prepared lots of exercises, and some of them are quite hard, and there are lots of them. So if you do not manage to solve, I did not write them in order for you to solve them all. Okay, maybe it's interesting for you to read all of the question statements, but I think it's beyond anyone's abilities to solve all of the problems. At least that would be my guess. There are really many problems. So rest reassured if you find that there are too many problems, or if you find that they are hard. And if you want to do something to prepare for tomorrow, I would suggest to have a look at the handwritten notes of chapter 1 on large deviations. And possibly also, if you want to think about the first exercise of the problem set, of the first problem set, that would also be nice. But yeah, I'll let you decide on this. Are there questions on what I just discussed? I mean, what I discussed over like today, not just in the last 5 minutes. Yeah, so if you, let's say that for now, try to read chapter 1 and do the first problem of the first problem set. Just to answer one question in the chat.
Oh, okay, yeah. So thanks, Jean-Christophe, for a great start for the school.